Well, I'm really honored and delighted to have been invited to speak at this conference in honor of Wolfgang Maya, who played a very important role in turning the math department at Stony Brook into a major center for differential geometry. And it's a real pleasure to be here to celebrate his birthday. The work that I'm going to talk about today is joint work with Hayo Hein, who is also a speaker at this conference, but who spoke about different work. When we wrote the paper, he was at the University of Maryland, but he's now changed to, he's about to start a new position at Fordham University in New York City. The paper is on the archive, and it has just appeared in the definitive final form online in Communications in Mathematical Physics. The paper version has not yet come out. But although I'm certainly very happy with the way that the final version looks, it's the same material is on the archive, and you won't have any problems with Springer trying to charge you ransom to see it. All right, so the topic that I'll be discussing today originated actually out of general relativity and concerns a very special class of non-compact complete Riemannian manifolds which look roughly like Euclidean space at infinity. Here I'm always assuming that the dimension of the manifold is at least 3, and therefore the nice picture you see is actually a fake picture. But on the other hand, it's the best picture I can draw. But keep in mind that this discussion often depends on having a real dimension at least 3. So a complete non-compact Riemannian n-manifold is called asymptotically Euclidean, or just for abbreviated AE. If there's a compact subset of the manifold such that its complement is diffeomorphic to Euclidean space of the same dimension minus a ball, in such a way that the metric roughly looks like the Euclidean metric. Namely, it looks like the Euclidean metric plus terms that fall off sufficiently rapidly. So you could make this definition for different fall-off rates, but the kind of the optimal minimal fall-off rate that I'll need is the metric differs from the Euclidean metric in the given asymptotic coordinate system. It falls off like 1 over so the radius to the 1 minus n over 2 power, or actually a little bit faster than that. And moreover, its first derivative should, so the first partial derivatives of the metric should also fall off at the rate you would expect for this power of the radius. All right, so.
Can you explain more color?
It looks a lot better if things are in different colors. All right, so the compact set we're throwing away is in blue, its complement is in red, the diffeomorphism and its target, which is Euclidean space minus a ball, is in black, and so forth. Okay, so now right now I've assumed that the complement is of this compact set is actually connected, only has one connected component. Oh, and sorry, there's one other hypothesis that one wants to put in. So I'll be denoting the scalar curvature in this talk is denoted by little s in red. And the crucial geometric hypothesis is that this is supposed to be an integrable function. It's an L1 function, so its absolute value is integrable. All right, so that's an extra fall-off rate, which involves now actually 2 derivatives of the metric. In the simplest version, one would imagine that you have a manifold such that when you cut out a compact set, there's only one connected component at infinity, or one end. But in fact, one can more generally consider manifolds such that when you cut out a compact set, there are finitely many ends, and each end is assumed to be diffeomorphic to Euclidean space minus a ball in such a way that the metric becomes asymptotically Euclidean. It looks like the standard Euclidean metric plus terms that fall off rapidly in infinity. Now, so of course, these different connected components of the complement of the compact set are referred to as ends. But it is very interesting, and it turns out to be important, to consider a generalization of this definition, which are so-called asymptotically locally Euclidean manifolds. And so, or ALE, it was obviously, this is a term coined by a group of physicists who obviously were out drinking beer at the time. An ALE manifold has almost the same definition as before, except that the ends, instead of looking like Euclidean space minus a ball, they look like Euclidean space minus a ball modulo a finite group of rotations. So because I've assumed that the real dimension is at least 3, these ends actually have finite fundamental groups, and a different way of saying it is that the ends have universal covers, which are the complement of a ball in Euclidean space. So each end is assumed to be of that type, but the fundamental group of the end, can change as you go from end to end. So you might have one end which looks like Euclidean space, another one might look like a cone over a complicated spherical space form with large fundamental group. And again, we have the same fall-off conditions. Now, by the way, of course, these are fake pictures, and I've drawn this end. It is, of course, in a technical sense, a cone over a spherical space form with the standard conical metric plus terms that fall off at infinity. But it's important to realize that while in dimension 2, such a cone would literally look like a paper cone that you would drink water out of, that you could get this by taking a sector of and making something which is just looks that would particularly embed in Euclidean space as a hypersurface. But in higher dimensions, you will never be able to, if you're trying to think of an example of what the metric looks like, don't make the mistake of taking a hypersurface in Euclidean space and expect it to look like one of these. If you take a cone over a sphere at an angle in Euclidean space, you get something where the sectional curvatures do not all fall off at infinity. Well, of course, you can embed this in Euclidean space with higher codimension. But keep that in mind. So these are cones in the obvious sense. These are the ends look like cones over spherical space forms plus terms that fall off infinity. But you shouldn't think of them as looking like a hypersurface in Euclidean space. All right. So the physicists, in thinking specifically about the asymptotically Euclidean case, and specifically thinking about real dimension 3, realized that there was an important invariant you could attach to such an end. The definition looks extremely peculiar at first, and it seems to be very coordinate dependent. You begin by taking, in this coordinate system, you take the divergence of the metric minus the gradient of its trace. So those are very coordinate dependent expressions. Then take the component of that in the unit Euclidean normal direction, facing out radially in Euclidean space. Then integrate that over a sphere of radius rho. Take the limit of that expression as the radius goes to infinity. And then, well, depending upon your taste, you might want to put in a standard normalizing factor. The one that the physical motivation would make most natural would be this particular number, gamma function over applied to the dimension over 2 divided by 4 over pi to the n over 2 times 4 times n minus 1. this particular constant is not terribly important for our discussion, but there are various ways you might want to try to normalize this expression. So here I'm doing something that is sort of a little bit contentious also. I'm taking, in the ALE case, where the n doesn't look like a cone over a sphere, but it's a cone over a spherical space form, I'm actually taking this, integral actually to be over the spherical space form of radius rho. So that would just introduce a factor of the order of the fundamental group of infinity. So here we've taken this peculiar integral of involving derivatives of the metric in that coordinate system and integrated over a spherical space form of fixed radius, taking the radius to infinity eventually. Nu is the outward pointing Euclidean normal vector, and it's been integrated initially in this definition against the Euclidean area form or volume in minus one dimensional volume form of that spherical space form in the coordinates. So this looks like just a very peculiar definition, and it looks like it's very coordinate dependent. However, in 1986, a mathematical physicist, Bartnik, and a relativist, Crucial, independently discovered that with fairly mild fall-off conditions, this was actually, this number called the mass is actually coordinate independent. So the minimal fall-off conditions that you need are actually these. These are the form that Crucial wrote down. Bartnik actually had a slightly stronger set of conditions, but they're pretty similar. So, but with these weak kinds of fall-off conditions, the mass is not merely well defined, but it's independent of the asymptotic coordinate system. If you take another asymptotic coordinate system and compute this number, it will be the same as long as you have at least this rate of fall-off. So no worse than that rate of fall-off. So here, a different way of saying what Crucial's fall-off condition is the difference between the geometric metric and the Euclidean metric in these coordinates is of class C1 minus tau, where the tau is the fall-off rate, and it's bigger than the dimension over 2 minus 1. Bartnik chose a very similar set of fall-off conditions with the same kind of rates of fall-off, but he actually assumed that the difference between the given metric and the Euclidean metric was in a certain weighted Sobolev space. So he assumed that. So here we're asking that that these are an LQ type these are LQ type conditions on the metric on the first two derivatives with fall off at this rate, and the convention is that as you take a derivative, you add, you subtract 1 from this fall off rate. All right, so actually Bartnik's condition is for his proofs with a little bit of slightly more modern technology. We could have instead put on a Halder type condition, saying it was, so Crucial was saying it's C1 minus tau. Bartnik's proofs, he gets a slightly stronger conclusion. And he would actually, it's enough to say that for some alpha bigger than 0, it's a class C1 alpha minus tau. So his condition, which is a Sobolev condition, seems to involve one more derivative, but this is what you actually need for the proof to work. It's just that the state of the analytic technology at that point was better for weighted Sobolev spaces than for weighted Holder spaces. All right, so what the heck is the motivation for this very strange definition? When n is equal to 3, if you have an asymptotically Euclidean 3 manifold, then you one context in which that could arise would be, it might be a space-like slice of a Lorentz manifold, and for simplicity, one assumes that the second fundamental form of that hypersurface in a Lorentzian form manifold is 0. Simply, one way of getting that is maybe it's a time-symmetric slice. Maybe there's an isometry that reverses the direction of time, and that's the fixed point set. In that case, physicists wanted to associate a number that would represent, you would think of this as the initial data for maybe some solution of Einstein's equation with some reasonable matter sources, and you would like to read off here the metric G in general relativity represents the gravitational field. Why do we call the metric G in differential geometry? It's Einstein's notation for gravitational field. Kind of peculiar, we always forget this. Never wondered where G came from. It was gravitational field. So the idea is that if you have an asymptotically flat three-manifold, something that looks very much like Euclidean space at infinity, that you should be able to read off from the asymptotics of the metric some effective apparent mass of an isolated system that you're looking at from very far away. And in particular, you can think of that as if you were to imagine putting an object in orbit very far away, looking at what the geodesics in space-time projected into this three-manifold for a short time. What would the apparent effective mass of this system be? So in particular, if you were to take a standard solution like the Schwarzschild solution or the Kerr solution, and you were to, oh, well, let's stick to Schwarzschild actually, you would actually read off the Schwarzschild mass. Kerr is a little more complicated because you couldn't take the second fundamental form of the hypersurface as being 0. All right, so so in any dimension, you can in fact, if you test out this definition on the simplest kind of Ricci flat Lorentzian n+1 manifold, which is the Schwarzschild solution, and it looks like this. Here I've written it in, oops, sorry. So here it has, it's invariant under the full orthogonal group in dimension n. And here, so we've got something that looks like the standard metric on the sphere times the radius squared. So that looks like the metric on a Euclidean sphere of radius rho. If this was the Euclidean metric, then you would also have just d rho squared, but you notice that in this formula, it's not quite 1 times d rho squared. It's 1 minus something involving a constant called the mass. And of course, here I'm talking about a Lorentz manifold, but we could just take the space-like slice. So we're looking at this metric. Currently, this is actually just defined on the complement of a ball well, it's defined on Sn minus 1 times the interval. So if you like, you could think of that as being a metric defined on the complement of a ball in Rn. And then you would find out that this number called the mass for this example would be just that number m. And it corresponds to the thing the physicists would call the mass. Now, for our purposes, we're actually investigating a problem in Kahler geometry, where using these ALE metrics come up very naturally as pointed Gromov-Hausdorff limits of rescaled versions of, for example, constant scalar curvature Kahler metrics. If you have a place where curvature accumulates, you zoom in on it in order to keep the curvature of constant scale. Then under certain circumstances, with the appropriate non-collapsing hypotheses, you can find that you'll get an ALE scalar flat Kahler manifold. And this mass term turns out to play an important role in various analytic problems. And I'll return to those in a moment. But the basic example here, where the metric is actually a Kahler metric, would be if you take C2 and you blow up the origin. So that means when you blow up the origin in C2, that actually means replace the origin with all of the complex lines through the origin. So that what the space you're actually looking at is the tautological line bundle over CP1. that tautological line bundle is a subbundle of the rank 2 trivial bundle, and it has therefore a natural map to C2. So you can collapse the 0 section in the O-1 line bundle to get C2. And there is an amazing metric on this, which is kind of the most obvious metric. I named it the Burns metric, because it has, Dan Burns was the person who noticed that if you take the most obvious metric on this blow-up, namely, so this maps both to C2 and to CP1. So pull back the Fubini's 2D metric, or just, if you like, the round two-sphere metric from CP1, multiply it by some constant m, and then pull back the Euclidean metric from C2 and add those together. Burns noticed that this is a Kahler metric that has 0 scalar curvature. It's a scalar flat Kahler metric, and it is actually asymptotically Euclidean. So again, there's a constant here. How big is that S2? The 0 section in this metric has some finite size. And the mass, as I've defined it, so here you could write it, if you like writing things in terms of Kahler potentials, then on the complement of the origin in C2, this metric can be written as I over 2 dd bar of, here I'm taking u is radius squared, so it's u plus 3m log u. And so that looks, this log term looks terrible, it blows up, and when you take dd bar of it, it turns out that the metric now falls off like 1 over r squared. So, in this case, this term, which if you're trying to use this metric, the log term might be a nightmare in various circumstances. How big the log contribution is exactly this mass. So when you're trying to expand a scalar flat Kahler metric at infinity, the first term that you see, this first deviation from the Euclidean metric is essentially something that looks like a multiple of this log term, and that constant is the mass in such examples. Now, this mass, of course, you may know, has played very interesting roles in mathematics. For example, it turns out that understanding the mass of certain metrics is crucial in Shane's solution of the proof of the final missing piece of the Geometr conjecture. So when you're trying to prove that every compact Riemannian manifold has a rescaling to constant scalar curvature, it turns out that you have to use, in certain dimensions, the fact that the positive mass conjecture is true. What is the positive mass conjecture? It says that if you have an asymptotically Euclidean manifold with scalar curvature greater than or equal to 0, then the mass will be greater than or equal to 0. Now, mathematically, so far from what I've said, this seems very, very non-obvious. The physical intuition that made this was a conjecture that was really made by physicists. And to them, it wasn't even stated as a conjecture, it was just something that obviously was true. The physical intuition is that, so the scalar curvature to them, the scalar curvature of the hypersurface in this setting actually represents the local mass density. And they're saying that if there's only if the local mass density is non-negative, then when you go out to infinity, the effective total mass will be non-negative. Now, keep in mind, of course, that relativity is a nonlinear theory. You can have, like in the Schwarzschild solution, something which is scalar flat. It has no local matter density, and yet the self-interaction of the gravitational field has produced a system which actually has positive mass. But their idea was that, yes, there was such an effect, but it should only make the mass bigger. It should not ever cancel. So as long as the local mass density is greater than or equal to 0, the effective mass that you would see at infinity should also be greater than or equal to 0. So the first proof of this was given by Shane and Yao, provided that the dimension of the manifold it was less than or equal to 7. And so their proof involves looking at minimal hypersurfaces, and there's an inductive aspect of the proof, and the failure of the regularity of minimal hypersurfaces in high dimensions obstructs their proof in general. Witten then gave a completely different proof in 1981. He was only interested in the three-dimensional case in his paper, but the thing he used is that oriented three manifolds are spin, so you could look at the Dirac equation, and in fact, his proof actually immediately generalizes to arbitrary dimensions, provided that your manifold is actually spin. Now, Hawking and Pope, and I'm not exactly sure who they had talked to, but they published a paper in 1978 where they already knew that that Shane and Yao had a proof of the positive mass conjecture. The fact that their paper came out earlier just reflects the fact that the refereeing standards in physics are quite different than in mathematics. In mathematics, the referee is supposed to sit on the paper until he or she is absolutely sure the thing is mathematically correct. Whereas in physics, the issue is whether it's on a hot topic and you want to publish it very quickly before the hot topic goes cold. So Hawking and Pope conjectured that this was true specifically in real dimension 4 in the ALE case. Already Hawking, in collaboration with people like Gary Gibbons, had discovered an amazing class of ALE Ricci flat four manifolds. And their conjecture was that those can be observed to have mass 0. The Ricci flat condition turns out to imply that the fall off to Euclidean is rather faster than you would get if you just assume something like the vanishing of the scalar curvature. And so they thought, well, maybe the same thing would be true, and if you were to take an ALE four manifold, that it should also always have, if you assume that scalar curvature is greater than or equal to 0, then it should have mass greater than or equal to 0. However, in 1986, I discovered a bunch of counterexamples to this conjecture. And for the benefit of the young people here, I'd like to quickly tell you an anecdote. I simply had written down a bunch of ALE scalar flat Kahler manifolds on line bundles over CP1. I thought they were very interesting. I had reasons related to twistor theory. I was interested in these metrics. And so I was very happy to have discovered these, knowing that they were not, these were things which could not be Ricci flat, but they were still scalar flat, and therefore a particular anti-self-aiding. So I sent this paper off to Communications in Mathematical Physics, and I got back a lukewarm referee's report saying, this is kind of interesting, but I don't really see what it's for, and I really don't think the authors pushed this far enough, and I don't think that this is good enough for this journal. So I was a young guy, I was not tenured, I was very depressed when I got this referee's report. So I went to my friend and colleague, Mike Anderson, I said, I think these things are very interesting, don't you? And he said, yeah, well, do you know about this conjecture of Hawking and Pope? Well, maybe you should calculate their masses. So I went out, he pointed out the paper, I read the paper by Hawking and Pope, I calculated the mass, it was negative. I sent I changed the title of the paper, changed the abstract, sent it back, and it was immediately accepted and published. So the moral is that when you're a young person and you're trying, nobody knows who you are. They've never heard of you. They're probably prejudiced against you because they don't even know who you are. You may get referees that are not very friendly, and they're not really giving you the proper chance. If you get rejected, don't get depressed. Just figure out what angle to emphasize in your work that will make it interesting to other people. The fact that you find it interesting yourself is not enough. You need to figure out where it fits into the broader scheme of things. All right, so these examples were scalar flat Kahler metrics, which were ALE. And they lived on line bundles of Chern class -3 or more negative over CP1. So they're kind of, in the case when the Chern class is -2, it's a Ricci. The corresponding thing is a Ricci flat metric, the Iguchi-Hansen metric. They're kind of cousins of Iguchi-Hansen. So this raises the questions: what can you systematically say in the Kahler context about the mass of ALE manifolds? The specific kind of question you might be interested in ultimately is, for example, if you know the complex structure, if you know the Kahler class, can you only have one scalar flat Kahler metric in that class? If that were true, then that information should determine what the mass is. So what happens, for example, in the scalar flat Kahler case? Well, actually, there's an interesting fact that happens just for ALE Kahler manifolds. They only have one end. So in the general ALE case, you might have many ends, and to each end you attach a mass. So when you're saying what's the mass of the space, well, it's not really a well-defined invariant of the space, it's an invariant of the end. But in the Kahler case, an ALE Kahler manifold can only have one end. So this kind of picture is what you might keep in mind. Here, keep in mind that when we're talking about the Kahler metrics, we must be an even real dimension, and for reasons which I regret in retrospect, I tend to call complex dimension M, which is not very good because mass tends to be called M, and one has to have different colors or different fonts. So questions about so notice that the complex dimension is in M. M is in blue, and then the other M is in a different font, and it's black. All right. So this little lemma, by the way, can be proved in various ways. Some are basically analytic. They have to do with the pseudoconvexity of the end at infinity. There's a more topological proof, which you can find in our paper, which I think is very cute, and it involves the fact that you can, it turns out that these manifolds can be compactified as complex orbifolds, and there is a natural intersection form on the 1-1 piece of the second cohomology, which has to have Lorentz signature, or it's a Lorentz type, and that would be a contradiction if you had more than one end, because you'd have more than one positive direction. Anyway, the upshot is that when you talk about the mass of an ALE Kahler manifold, it's an unambiguous thing. It does not depend upon the choice of n. So I'm going to now focus for a moment just on scalar flat Kahler manifolds. I mentioned there were some examples where I had calculated by brute force what the mass was and had gotten an answer that some people found surprising. But the point that I discovered in this work with Hayo is that the mass of an ALE scalar flat Kahler manifold is actually a topological invariant. It depends, so the mass black Zapfino M of the manifold red M. Sorry, you were wondering why I have a color scheme. Now it starts to become clear. Right? The mass is completely determined by knowing what the underlying smooth manifold is, what the first Chern class of the complex structure is, and what the Kahler class of the given metric is. And in fact, so this theorem is merely promising that there's some relationship that we actually will see in a minute, that there's an explicit formula. It's not, this is not some piece of black magic. I'll show you what the formula is in a moment. So this explicit formula in particular reproduces the things that you can grind out by hard work, by hand. And in particular, as soon as you've got this new set of spectacles to put on, you can start pulling known examples off the shelf and saying, oh, what's the mass of this, that, and this? And so there were examples that I had written down that were more complicated. Specifically, you can take a blow-up of one of these line bundles at a bunch of points. I've never bothered to calculate the mass of those metrics, even though the metrics are fairly explicit. And the following amusing thing happens. You can arrange for the mass to be 0 without making the Ricci tensor 0. So Claudio Arezzo had been hoping that it would turn out that there was some kind of converse statement to the fact that in the Ricci flat Kahler case, the mass vanishes. He was hoping that, on the other hand, if the mass vanished, maybe it would have to be Ricci flat. It's certainly not true. And in fact, there are infinitely many topological types of ALE scalar flat Kahler surfaces, where surface means complex surface, complex dimension 2, real dimension 4, with zero mass, but which are not Ricci flat. Now, in fact, after we made this observation, we were very excited and pleased. My student, Joanna Shuvina, then contacted us and said, well, if you read a paper by Roland and Singer very carefully, they actually, by brute force, calculated some example where this happened. And so we were less excited about this application afterwards. But it's a typical this is a typical example of the fact that it's very convenient to have some topological formula for the mass. So it's a topological invariant, and we'll see now how it goes explicitly. So to give you an explicit formula, I have to first point out a little topological fact. So if you have an ALE manifold of any real dimension at least 4, then if you look at the natural map on the second cohomology with compact supports, so I mean there's a complex of differential forms with compact supports, and you have the compactly supported cohomology, but there's a natural map from the compactly supported cohomology to the ordinary de Rham cohomology. And the statement is that on H2, at least if you're in dimension at least 4, this is an isomorphism. So just to quickly remind you what, so there's a complex of compactly supported differential forms, and D makes it into a cochain complex. And there's also a natural map from compactly supported forms to all smooth forms. And so under this natural map, you get an isomorphism for this class's basis between the compactly supported cohomology and the usual cohomology. Now the reason that's useful is that the compactly supported cohomology is Poincare dual to the usual cohomology in complementary dimensions. So if you're in dimension n, you can pair a compactly supported 2 class with an n-2 class in de Rham cohomology in the usual sense. So the proof of this is actually fairly straightforward once you know that if you were to take this non-compact manifold and turn it into a manifold with boundary by adding a spherical space form at infinity. Here I'm just doing, imagine that there's only one n, but actually this proof works even if there are many n's. The compactly supported cohomology is actually the same as the relative cohomology of the manifold with boundary relative to boundary. And then this really just comes down to, if you look at the exact sequence of the pair, and you remember that the boundary, you're adding is a spherical space form, it's not going to have any first or second cohomology, then you automatically read this off. All right, so this map from compactly supported cohomology to ordinary cohomology in dimension 2 is an isomorphism, and therefore we can talk about its inverse. And if you can talk about its inverse, why don't we introduce some notation for it? So the notation that I'll use is club. And the reason is that if you have some closed 2 form, you can club it over the head until it's compactly supported, and then that will be the corresponding compactly supported class. All right, so this is just the inverse of the natural isomorphism that you get by inclusion of compactly supported forms into all forms. Okay, so once we have that piece of notation, we can state this the mass formula. And actually, I've been talking about this in the scalar flat Kahler case, but let's just do it now for an ALE Kahler manifold. For any ALE Kahler manifold of complex dimension m, blue m, has mass, in black, given by the following kind of expression. So first, you look at the integral of the scalar curvature. Remember, we've assumed the scalar curvature is integrable, so that makes sense. And then that's multiplied by a certain constant, positive constant. Then you look at the pairing of club of the first Chern class with the Kahler form to the m-1. And then that's divided by a certain constant. All right, so that is the general formula for the mass of an ALE Kahler manifold. Okay, so again, remember, S is the scalar curvature. It's being integrated against metric volume form. C1 here is the first Chern class of the complex structure, and omega is the Kahler class. So there's a 2 form associated with a closed 2 form associated with the Kahler metric, and it has a class in the second homology. And so the brackets are just the natural pairing I mentioned before that comes up in discussing Poincare duality here. It's just you just wedging a compactly supported form with a closed form, and it makes sense to integrate. All right, now this formula for the mass looks very peculiar at first, but actually, it actually might look a little bit better if we moved a constant to the other side. So a certain multiple of the mass is actually the difference between the integral of the scalar curvature and So you could think of this as involving the scalar curvature minus some multiple of club C1 paired with the m-1st power of the Kahler class. Now, the reason that's an interesting thing to look at is that there's a beautiful formula which generalizes from the familiar two-dimensional Gauss-Bonnet, which is true for compact Kahler manifolds of any dimension. So usual two-dimensional Gauss-Bonnet would say if you integrate the scalar curvature, well, that's the same as the Gauss curvature up to a factor of 2, then that's related to the first Chern class of the thing thought of as a Riemann surface, but that's the same as the Euler characteristic, right? The way you generalize that is that the integral of the scalar curvature of a compact Kahler manifold is gotten by pairing the first Chern class with the m-1st power of the Kahler class. So you get this formula for a compact Kahler manifold. You have this identity, that scalar curvature plus this multiple of C1 and paired with omega the m-1 is 0. Well, in fact, this mass is actually the degree to which that formula is not true in the ALE case. It's, if you like, a defect or an anomaly in that formula. So it's a sort of boundary correction to that, to trying to understand if that would correctly compute the integral of the scalar curvature in the compact case. All right, so here's the formula that I announced before, that the mass is given by this topological term involving just the first Chern class and the Kahler form, or the Kahler class, and the integral of the scalar curvature. So in particular, if your manifold is scalar flat, the integral of the scalar curvature obviously vanishes then, and you get that the mass is a topological expression, just determined by the first Chern class and the Kahler form, or the Kahler class. So the previous statement I made about the topological invariance of the mass is an immediate consequence. All right, so I'm going to give you a very rough idea of the proof. This is sort of the first sketch that Hayo and I came up with in order to get this mass formula. So, but this is going to, so I'm going to be working in a very special case with some slightly artificial assumptions. So I'll first of all assume that the complex dimension is 2, and so in other words, the real dimension is 4 in this little argument. For simplicity, I'll stick to the scalar flat case. I'll assume, and this is the place where there's, so the first two things, those are things we were really interested in. The next assumption is that we'll assume that we know that diffeomorphically, by assumption, the thing looks like Euclidean space at infinity. Does it look like C2 with its standard complex structure at infinity? Let's just assume for the moment that it does. There are examples in which that's true, but there are also examples in which it's false. All right, so rather than just assuming that we have a diffeomorphism between M minus a compact set and C2 minus a ball, divided by some group, let's assume that it actually is a biomorphism. All right, so the metric G is Kahler, and one thing that happens for a Kahler metric, or more generally for a balanced metric, is that the complex coordinates are actually harmonic with respect to the Kahler metric. The Laplacian has a very simple formulation for a Kahler metric in terms of the trace of dv bar. Holomorphic functions are actually harmonic, and in particular, the real parts of the complex coordinates are harmonic. So in fact, the real and imaginary parts of the complex coordinates give you a harmonic coordinate system. It turns out that, so in particular, when one was looking at that strange integrand, which involved the trace, here I've made it the metric trace, it could have been the Euclidean trace, of basically, we're looking at divergence of the metric minus the gradient of the trace of the metric. That actually starts looking like something that's a little bit more geometric and natural. In these coordinate systems, we're looking at the volume as a function with respect to the coordinate system. So you're taking the thing that you would multiply the Euclidean volume form by to get the metric volume form. And then you're simply taking log of that, then taking d, then Hodge star with a -1, up to some terms that fall off at infinity fairly quickly. And so if you were to, you look at the definition of the mass, this is still an unnatural looking thing because we're measuring the volume of the metric with respect to this coordinate system, with respect to this complex coordinate system, but this looks a little bit more geometrically recognizable now. So it's you're basically taking star d log of the volume form. But the interesting point is that the volume form also, log of the volume form also comes up in Kahler geometry in computing the Ricci tensor, specifically represent, or the corresponding 1-1 form that's called the Ricci form. So if we look at the 1 form gotten by I over 2 round d minus d bar of log of square root of that g, then that's actually a real volume form. This is a real 1 form whose exterior derivative is the Ricci form. So that, in other words, that's the Ricci tensor with a j stuck in one slot. And this also has the property that if we take the integrand that appears up here, it's actually twice that 1 form wedged the Kahler form. So this says that the mass is the limit of integrals on these large space forms, or large spheres if you like, to keep it simpler, of that 1 form wedge the Kahler form. But on the other hand, I'm assuming for the moment that the scalar curvature is identically 0. So that means that if you take d of this 3 form, theta wedge omega, you'll get, since omega is closed, this becomes the Ricci form wedge omega. That's the trace of the Ricci form. That's the scalar curvature, essentially. And that vanishes by assumption. So, we've actually, rather than taking a limit in this scalar flat case, you could have just integrated this 3 form over any sufficiently large sphere. You just take some sphere out in your infinity. It doesn't matter which one you take. You're just taking that. There's a 3 homology class in the end. And we have some closed 3 form that's just defined on the end. Remember, to get this 3 form, it's not. We still use the coordinates somewhere to produce this theta. All right, now we wanted to reinterpret that formula as something really natural. And the way you can do this is take a smooth cutoff function, which is 1 near infinity and 0 outside of this end. If you do that, so this is identically 0 away from the end and identically 1 near infinity. All right, so if we then let's introduce a manifold with boundary, which where we just cut off our non-compact manifold at some very large radius where that radius is large enough so that our cutoff function is identically 1 in that region, okay, the region beyond. So here's the picture. We're going to reinterpret the previous integral using Stokes' theorem. So here we have, if you take the Ricci form minus df theta, so theta was only defined on the end, you multiply by the cutoff to get a well-defined one form on the whole manifold. So look at rho, the Ricci form minus df theta. This has the property that since f is identically 1 near infinity and d theta is the Ricci form, this is a compactly supported form. In fact, so this is exactly what you get by applying this club operation. We've taken the Ricci form and we've clubbed it over the head to make it compactly supported. But that the Ricci form represents 2 pi times the first Chern class. So this is giving us 2 pi times club of the first Chern class. This is a concrete representative of it. And so just by definition, the pairing is you would take wedge, this form psi, wedge omega, and we would integrate it. Well, a priori, we're integrating on the entire non-compact manifold, but it's just supported in this manifold with boundary. But now, you can apply Stokes' theorem, because here you have this, so you have the integral on this manifold with boundary of rho minus df theta wedge omega, but it's scalar flat, so that says that rho wedge omega is 0. And so therefore, this is just the integral on the manifold with boundary of df theta wedge omega. You apply Stokes, and you get an integral on the boundary, which, remembering that f is identically 1 in that region, is exactly the formula we saw before that gave the mass. And so the conclusion is the mass, which we previously expressed in terms of the integral on the large space form of theta wedge omega, is in fact just a multiple of club C1 with the class of omega. And here there's a misprint here. That should be the class of omega, not the form. So in this argument, we assumed that the complex dimension was 2, the metric was scalar flat, and the complex structure was standard at infinity. Now for the general case, well, we want to first generalize this to complex dimension greater than or equal to 2. This is pretty straightforward. I mean, it's just a matter of replacing omega with omega's appropriate power. Well, in general, the scalar curvature, we don't want to just assume that it's identically 0. But I mean, you just have to you do have to just add a compensating term, which involves the integral of the scalar curvature. So if you just push through the same argument, it naturally adapts as long as you remember to add in this multiple of the integral of the scalar curvature. Now, the other assumption. So these, getting from where we were to where we want to be is not so bad in terms of dropping the first couple of assumptions. But what about the assumption that the complex structure is standard at infinity? It turns out that if you're in complex dimension bigger than 2, this always happens. It's a theorem which you can find proven in our paper that for an ALE Kahler manifold, if its complex dimension is bigger than 2, J is actually standard at infinity. It looks just like standard complex structure on CM modulo group. But when m is equal to 2, well, when m is equal to 2, and if it's asymptotically Euclidean, you can still show that J is standard at infinity. But the argument has a different flavor. It's a global argument rather than a local argument in the end. But in the general ALE case, when m is equal to 2, J can be non-standard at infinity. So this is a serious issue. And it's actually, so the technically most difficult parts of our paper relate to this issue. So to see that it's a serious issue, you only have to look as far as the so-called Iguchi-Hansen metric. Now, the Iguchi-Hansen metric is a Ricci flat Kahler metric, but it's actually hyper-Kahler. It's actually Kahler with respect to a family of complex structures. One of those is the standard complex structure on the O-2 line bundle, the Chern class -2 line bundle over CP1. A different way of saying that is you could take a quadratic cone in C3 and blow up the origin. take the proper transform, you would get that space. There are two of the complex structures compatible with Iguchi-Hansen metric have that complex structure, and that one is actually standard of infinity. But on the other hand, there's a family of complex structures, and most of them instead look like affine quadrics, and they're not. The complex structure is not standard of infinity. Now, for Iguchi-Hansen, or for more general hypercalometrics, you could say, well, okay, just try to see if you can choose a clever complex structure. But this is a serious issue. You can't get around it that way because, for example, on the there are deformations of the O-3 line bundle discovered rather recently by Nobuhiro Honda, which are also they're scalar flat calometrics on these non-trivial deformations of the O-3 line bundle. In fact, you can deform the O-3 line bundle as an affine bundle. So just in the Iguchi-Hansen case, the quadrics are ruled. You can actually think of it as a bundle. It's still a bundle of complex lines over CP1. Here, the same thing is true, but the lines don't have a vector space structure. They're just affine spaces. So the things get seriously messed up. So the first argument that we found to solve this problem was that we showed, actually by assuming a little bit better fall off, assuming that instead of assuming something involving C1 alpha, instead of assuming C2 alpha behavior, we could show that on the metric, we could show that the almost complex structure, while it doesn't coincide with the standard complex structure, you can choose coordinates in which it looks like the standard complex structure, but plus terms that fall off, at least like radius to the -3. And that's enough to make the argument work. We actually eventually found a better argument. It's much harder, but it involves very little regularity where we don't have to use quite these asymptotes. Okay, so how do you understand the behavior of the complex structure of infinity? If you take the universal cover of an end, one way you can approach it is to say the universal cover of the end, well, that basically is something like, roughly looks like Cm. It's definitely, you know, R2m minus a ball with a complex structure that you can show kind of falls off to the standard one. It kind of falls off to a constant coefficient complex structure. And that is enough to allow you, with the given hypotheses, to add a CPM minus 1 at infinity and actually show that what you've got is a complex manifold. So you can actually take the universal cover of an N and you can attach a hypersurface at infinity in such a way that this actually becomes a complex manifold. And that is actually a CPM minus 1 with normal bundle O of 1. So Kahler's theorem tells you that you can move that. It belongs to a family of hypersurfaces. In high dimensions, you can actually use this to show up. If you look at a family of hypersurfaces, it carries a natural projective structure with the property that, so the holomorphic projective structure with the property that it has many totally geodesic complex hypersurfaces. So there's a sort of classical projective geometry due to Schouten and Zweig that such a thing is flat if you're in dimension bigger than 3. But in dimension m, if it's on a surface, you're just saying it has lots of geodesics in it. It doesn't tell you anything. And that's actually, so in fact, there's a projective Coton tensor that can be non-zero in that dimension, and that's really the reflection of the source of the problem. On the other hand, this way of looking at things does tell you that things are actually flatter than you might have expected, because this Coton tensor is actually something that involves it's something that involves a derivative of curvature. So there's one approach to understanding things that way. So in the asymptotically Euclidean case, you can actually compactify the manifold itself by adding a CPM minus 1 at infinity. And something very interesting comes out of that. First of all, in complex dimension 2, you get a compact complex surface that contains a CP1 of self-intersection 1 and such a thing has to be a rational surface. In fact, it has to be below of CP2 at points away from a line. In higher dimensions, you get, this is a base-free linear system of hypersurfaces. You can prove that they all belong to the same. The divisor of one of these hypersurfaces also cuts out all of these others. They have the same divisor line up. So they belong to a linear system. And this gives rise to a map of your compactified object to CPM minus 1. If you cut out the hypersurface at infinity, what you've said is that in some generalized sense, your manifold, if it's AE in Kahler, it's actually going to be, as a complex manifold, it's a modification of CPM. You've just collapsed some subvarieties. That has some very interesting consequences because I mentioned before the positive mass theorem. We knew how to prove, known proofs are known if you have a low-dimensional manifold or a spin manifold, but you might ask it, it's still interesting in the Kahler case, in general, in high dimensions. In fact, one consequence of this work is that if you have an asymptotically Euclidean Kahler manifold, notice this is not asymptotically locally Euclidean, asymptotically Euclidean. So for asymptotically Euclidean manifolds, assuming that infinity is simply connected. If the scalar curvature is non-negative, then the mass is non-negative. Okay? So asymptotically Euclidean Kahler and scalar curvature greater than equal to 0 implies the mass is greater than equal to 0. Moreover, if the mass is 0, then the thing is flat. It's actually Euclidean space, complex Euclidean space with standard Kahler metric. But the proof, interestingly enough, I mean, that's kind of cute. This was not known in general, but actually, we don't just prove that the mass is positive, we actually give an effective lower bound. So we get what we call a generalized Penrose inequality. In relativity, the Penrose inequality would say, if you had an asymptotically Euclidean 3 manifold, then you can try to, there's a lower bound for the mass in terms of an area of a minimal surface, minimal submanifold. Now here, this is a little bit of a parody of the Penrose inequality. We get minimal submanifolds, but they're complex codimension 1 rather than real codimension 1. So what we find is the following. If you have an asymptotically Euclidean Kahler manifold with scalar curvature greater than or equal to 0, then this asymptotic Euclidean manifold carries a so-called canonical divisor. So there is, you can write its canonical class as a sum with non-negative, with positive integer coefficients of a collection of complex hypersurfaces. And if the manifold is not CM, this collection of complex hypersurfaces is non-empty. There's at least one of them. And in terms of this divisor, the mass is bounded below by the volume of those hypersurfaces with those multiplicities, which are positive integers, times the universal constant. Equality happens in this case if and only if the manifold is scalar flat Kahler. So the simplest kind of example would be if you take C2 and you blow it up at a lot of points, then you would have a manifold that admits scalar flat Kahler metrics, and it would have a lot of CP1s in it. And it would say that the areas of those CP1s times the universal constant is a lower bound for the mass. And it's saturated if and only if the metric is scalar flat. So if you took some other Kahler metric which just had non-negative scalar curvature, then you would get even more mass. So the proof is basically, we already have this map. This is a silly proof once you see it. We've constructed by hard work a natural map of the manifold to CM. It can be collapsed to CM. On CM, you have a natural top degree holomorphic form. You pull it back. Where does it vanish? It vanishes at the critical points of that map. In other words, the things you've collapsed. And those hypersurfaces are given. They're cut out by the vanishing of this form, and the multiplicity of the vanishing gives you those positive integer coefficients. Okay, so now the point is that divisor exactly represents, it's the canonical class that's minus C1, and here you see minus of C1. That's exactly the term that comes up with the mass formula. All right, so here's the general mass formula for you to meditate upon. And so this is a statement about more or less topological formula for any asymptotically locally Euclidean Kahler manifold. And so I'm essentially done now, but before ending, I would like to say two more things. Herzlichen Glückwunsch zum Geburtstag, Wolfgang. E grazie a tutti gli organizzatori di questo bellissimo convegno.
Thank you very much for this great talk. Are there any questions or further comments on the Kahler scheme?
I have actually a question from your first slide.
Okay.
But actually, before your first slide, do you have any...
If I back it up, will anybody have an epileptic fit?
No, you don't need to. You don't need to.
My first slide was the title. That's a question about the title. Color scheme for the title?
Do you have a geometric interpretation of asymptotical Euclidean that is not analytic, just saying that there exists a coordinate system such that, even if it is strong, something that stronger implies, but geometric?
Well, it's a bit imprecise, okay? But the key thing the point is that these are objects which naturally occur as rescaling limits of Kahler manifolds. You take sequences of Kahler manifolds and you're accumulating curvature somewhere. And if you have mild hypotheses that avoid collapse, say it's control of the Sobolev constant, then this kind of fall off is guaranteed. Another way you don't get these hypotheses for free. In fact, if you were in the specific case of Ricci flat ALE four manifolds, there is a beautiful theorem which says that you get this kind of fall off if and only if the volume growth is roughly the same as in Euclidean space. So in Euclidean space, real dimension 4, complex dimension 2, the volume of a large ball will grow quarterly, right? So if you have that, so if you have a volume of a large ball in the manifold, so take a large distance ball, you could ask. So the typical sort of thing is that in these manifolds, the volume of a large ball is like it would be in Euclidean space. Now, it's not a theorem you need some hypotheses about the metric before you can go from that geometric statement to saying that it's actually ALE. But the first thing that you should sort of think about is, does the volume of a large ball grow asymptotically like it would in Euclidean space? That's one characteristic of these manifolds. By the way, that's used in an amusing way. So I said, characterizing the flat metric, the fact that if you're in the asymptotically Euclidean case, it's not just that you would have, so in the ALE case, the volume of a large ball is some constant times the radius to the fourth power. But in the asymptotically Euclidean case, the constant is the same as it would be for the Euclidean metric. If you already know that the thing is Ricci flat, Bishop-Bromoff automatically tells you it has to be flat space, because otherwise the volume, there's a monoticity on volume growths. So if you've already got to the point where you know it's Ricci flat and you have this volume growth, you'll conclude that it's the flat metric. But the fact, so you might say, well, why consider ALE rather than asymptotically Euclidean? If you're interested in things that are Ricci flat, you're not going to see anything that's not flat if it's asymptotically Euclidean. But if it turns out that there is this wonderful world of asymptotically locally Euclidean Ricci flat metrics in dimension 4. One of the big research topics right now is to try, suppose the volume growth is a bit slower. Can you classify the metrics? People have made amazing progress in recent years on this kind of problem. I hope that's enough. It's not really an answer to your question.
Okay.
Maybe you should pose this to yourself or your students as a research problem, but you want to. I've just told you what happens in the asymptotically ALE case if it is Ricci flat, and you might want to try to prove a theorem about scalar flat Kahler metrics with a certain volume growth condition. Hope that they would turn out also to automatically be ALE in this precise sense.
So if there are no more questions, then before I hand over to Wolfgang Meyer, who wants to say some words, let's thank again for LeBrun, all speakers.